Our project is Outdoor Space Cooler. I'm Kyle. My teammates are Brendan, Kevin, Raymond, and Joseph. Our advisors are Dr. Alvandi and Dr. Wulandana, and our main sponsor is Rockwell. The problem we are trying to address is hot outdoor seating areas. During the summer, especially in restaurants, resorts, sporting events, and residential spaces, they lose money due to these uncomfortable conditions. So our solution, implement a two-stage cooling system. The first stage will incorporate an evaporative cooling system. The second stage will be an air conditioner. Efficiency and comfortability will be increased by using solar panels, as they will cut down on energy consumption as well as provide shade.
Hi, my name is Kevin Harjes, and I'm a mechanical engineer. I worked on the psychometrics and the rendering of this design. So starting with the psychometrics, if you can see from the chart, the combination of these processes work in all climates. For example, New York is wet and warm, while Texas is relatively hot and dry. Evaporative cooling works better in the drying conditions, as seen by the length of the blue line. The control system will increase airflow through the stage if conditions are dry to reduce power consumption. Air conditioning works better in wetter environments, so the controls will increase air conditioning power in these conditions. Condensation on the evaporative coil removes some moisture. The final state is comfortable 70 degrees relative humidity and 20 degrees Celsius. The rendering of the design was made after multiple designs to decide on the best. We also received some feedback from the public. The final rendering incorporates aesthetic and portability with a combined seat and canopy structure. It is also designed to be lightweight and weather resistant.
Hi, my name is Raymond, and I'm a computer engineer, and I worked on the control system for the outdoor space cooler. Moving on to our control system. For the input of our control system, we have the temperature and humidity. We are using a fuzzy logic-based control system for our design in order to achieve a lower power consumption. The logic flow of our design starts with the user. The user sets the desired temperature. Then the system compares the ambient temperature with the desired temperature and also reads the humidifier and acts accordingly to our fuzzy logic flow. If you look at the first row, you can see that when the temperature is too cold and the humidity is dry, the compressor will be turned off, the fan will be turned off, and the fin direction will be pointing away. And also moving on to the next table, the table shows the numerical values. And moving on, this system is able to analyze temperature and humidity and output the required protocols for the compressor speed, fan speed, and fin direction in order to reach the desired climate. Therefore, the energy consumption of the unit is further reduced by providing the most efficient logic for each condition and sending power to where it is necessary.
Hey everyone, my name is Brendan French, and I will be discussing the experiment results / simulation results section. To test how the refrigeration cycle in our design would react to constant high temperatures, a 400 square foot room was heated to approximately 30 degrees Celsius using a wood stove. Next, a 4-channel thermocouple temperature logger was attached to different locations on the air conditioner that was used in the design. Channel 1 read ambient room temperature. Channel 2 read the temperature of the air coming out of the evaporator blower, which is the conditioned air. Channel 3 read the temperature of the evaporator coil. And channel 4 read the temperature of the exhaust air coming from the condenser fan. Key results from this experiment include a change in temperature from inlet to outlet of approximately 16 degrees Celsius, which is 28.8 degrees Fahrenheit. Also, a clamp meter was used to measure the amperage that the system was using, and from this measurement, the power consumption was calculated to be 1,430 watts. So moving on to the simulation result, ANSYS, a finite element analysis software, was used to create a simulation of the temperature profile of the airflow through a pipe insulated with a 1/2-inch thick Rockwell bat. The air temperature surrounding the pipe was set to be 40 degrees Celsius or 104 degrees Fahrenheit. The air inlet temperature, air coming from the evaporator blower, was set to be 10 degrees Celsius. The temperature profile from inlet to outlet was then observed as the air velocity was increased from 0.1 meters per second to 0.4 meters per second and finally 1 meters per second. It could be seen as the velocity of the air was increased. The change in temperature from inlet to the outlet decreased from approximately 15 degrees Celsius with the air moving at 0.1 meters per second to practically no change in temperature with air moving at 1 meter per second. During the test previously discussed, the measured air temperature coming from the evaporator blower, inlet air in the simulation, was 8.3 meters per second. This is significantly higher than the maximum simulation velocity, indicating that the actual temperature gradient of the outlet pipe is negligible.
Hi, this is Joseph Marchese. So, in order to estimate the total cost of the materials for the outdoor space cooler, a table was created which can be seen in the center of the poster board. The cost per quantity was estimated using online resources, and the number of these products was determined through analysis of our unit. The overall estimation for the unit can be seen at the bottom to equal out to a little above $1,000. There are many key features that we wanted to implement in our final design that could not come to fruition due to the coronavirus. The first component includes attaching solar panels to the canopy and integrating the power generation of those solar panels to the overall power supply of the system. We then want to incorporate a passive dehumidification system before the inlet of the evaporative cooler. This will result in higher thermal efficiency of the overall system. LED lights will also be attached in the canopy for nighttime use, while USB charging ports will add convenience for consumers. Finally, the canopy structure will have an attached outlet fan and brackets to mount the solar panel.